So, we are back with this equation here. So, we started off with D'Alembert's principle, which is here, and we took the first term. There are two terms in D'Alembert's principle, the first term and the second term, so, or rather one of this term. So, we took with this term there, which is pi dot delta xi. Please remember, there is a summation convention explicitly, I mean it's which is not written explicitly, but on the repeated index is there. So, which is essentially pi dot, that means mi xi double dot. I hope it is clear, two dots, which we could write in this particular form, which is ddt of mi xi dot del xi del qj, okay. And also we have to understand that this is a double sum of I and j, am I right? Yeah. So, it is a double sum of I and j, yeah, and this whole thing will be multiplied by del qj, okay. So, this whole thing will be multiplied by del qj or qk, I mean whichever index you want to use, we can use j or we can use k, right. So, let us first get rid of these summations which are already implied, because I is a repeated index, j is also a repeated index. If you want, let us keep to just to maintain the clarity, we can use k instead, because in the last lecture also I remember we used k. Does not matter, because these are dummy indices anyway. So, we can either use j or k or any other number which is not I. Now, what we did from here, we said that okay, so this is my velocity, and there was a result that we can equate this with this. So, we did that in the last class. So, this is a velocity term, this is also a velocity term, and we could write the first term as ddt of del t del qk dot, okay, where t is given by half mi vi square, where vi is xi dot. So, we can also write xi dot square, okay. These are not generalized coordinates, but it is a sum over all the Cartesian coordinates of the system, and if we want to express it in terms of generalized coordinates, t will be simply half mi qk dot square, right. So, sorry, q, right, or mk, sorry, index has to match mk qk dot square. So, good thing is your kinetic energy is frame independent. So, whether you express it in terms of the Cartesian coordinates or you express it in terms of some generalized coordinate, it does not matter, your t remains your t, the total kinetic energy is invariant. So, the first term is might as well can be written in this particular form. For the second term, see this again, it can be shown that this ddt can be taken inside, and this whole thing can be written as, so ddt of del xi del qk can be written as del xi dot del qk. I mean it is again, once again it is not very straightforward, but it can be shown in two steps. I am just leaving it to you, because so that you can get a better grip on the subject. If you can prove it yourself, it is also there in the any standard textbooks, you can have a look, but these are not very difficult. So, using this, what we can do is we can get rid of this ddt term here, put this on xi, right. So, once again this is an xi dot, this is xi dot. So, we replace it with vi here and vi here, and we identify this term as time derivative of, or not time derivative, but derivative of t with respect to qk. Once again t is equal to half m, this the same thing mi Vi square or xi dot square, right. So, this identification helps us in writing this equation, the first term of D'Alembert's principle, first term in this particular equation as this, and this whole thing will be multiplied by delta qk, right. So, if we go back to D'Alembert's principle, we have two terms, there is, or rather actually it is a combination of many terms, each term has two aspects of it. So, what we did is we separated out all the pi dot sums and we have shown that it has a general form assuming all the summation is going on. Now, there is no summation over xi anymore, all the xi's are included, all these sums are included in this T, and kinetic energy is frame independent. So, we can might as well express in terms of qk, does not matter, kinetic energy is a constant, sorry, not a constant, but it is a quantity that we can measure in any frame and we can express it in any coordinate system we want. So, most important thing is this whole thing has reduced to this particular form where the only variables are the generalized coordinates and the whole thing is multiplied by a delta qk. Now, for the other term, this term, okay. So, we have sum over I fi dot delta xi, right. These might as well be written as just like we did in the previous case. Okay, once again, first let me start by removing the summation symbol here. Fi dot delta xi implies summation. So, we can do fi, what we can do is we can write fi delta xi delta qk or del xi del qk delta qk. Okay. So, putting it in terms of generalized coordinate, and fi, if you recall, if there is a potential function, let us say we are talking about conservative forces, there could be two types of force in general, there could be a conservative force, there could be a dissipative force, right. So, let us assume that for now we are not, I think we have discussed it already, we are assuming that there is no dissipative force acting on the system as of now. Okay. How to handle that situation, we will come slowly and slowly we will see. Right now, let us assume that these fi's are conservative in nature. If this is conservative, then every force can be written in terms of some potential function, right. So, each of the force components can be written as a function of time derivative of some generalized potential component, right. So, if we substitute for it, just give me a second, or rather I would use grad, that will be better, probably. Is it okay to use grad also? Actually, grad means the same thing, just give me a second, yeah, better to use grad. So, it will be grad I v. So, that is the most general. So, if so what we call, if I break it into components, I get the same thing. So, if I put it here, so it will be minus grad I v del xi del qk delta qk. Now, or actually there is another way of doing it, let us do it this way better, because it will be bit confusing, because the calculations are, there are many steps which we can avoid. Okay. So, what we can do is we can define this term as a generalized force q k, and then we multiply this with a delta qk. Okay. So, we can have a generalized force term which has this particular form. Now, this is a definition of a generalized force. So, what we did here, we have a force component measured in Cartesian coordinate, and then we have a basically a transformation term. It can be shown that this is actually one of the elements of the Jacobian transformation matrix, which we are not going into details. But so essentially we are taking this force component and converting it to a component which will be one equivalent component in the generalized force or generalized coordinate dimensions. Okay. So, this quantity is called the generalized force term. Now, it is not only force, please understand now, this is the force multiplied by a displacement, although a virtual displacement, it is a displacement. So, this whole quantity is called generalized work. So, this equation, all the terms has the dimension of work. So, here now if you recall what did I tell you, that generalized coordinates need not necessarily have the dimension of coordinates. Similarly, generalized velocities need not necessarily have the dimension of velocities, and generalized force, which is this term, need not necessarily has the dimension of a force. But the criteria is the generalized work has to have the dimension of work. In real life, what is the dimension of work? It's force times so Newton times meter, for example. So, generalized force has to have this dimension, proper dimension of force, so that this equation, I mean, please remember, it is a transformation of the same force equation we wrote in a standard Cartesian coordinate system. Now, if this is my generalized force, what I can do is I can add this term into this equation, and we can write this as right. Instead of closing the bracket here, we can add this term, which will be with a opposite sign, because there is a sign difference between these two terms. So, it will be minus qk delta qk. Okay. So, now this comprises my full, I mean, transformed form of D'Alembert's principle, transformed into generalized coordinate space. Now, this qk, because it is a generalized force term, we can of course define a potential function for it. The thing which I intended to do in the real space and then transform, that is not required. I mean, we can do it that way, but this transformation will be little more complicated. What we can do is, now we can start writing this qk as minus del v del qk. So, instead of defining this potential, I mean, force in the Cartesian coordinate system and transforming the whole thing, I am writing a the force as a function of, I mean, as a differentiation of potential in the generalized space itself. That is very well justified, because finally we will see that we will be working in the generalized coordinate framework only. So, it is okay if we define it like this. Now, if we do that and we slightly rearrange this, then my equation looks like minus del qk t minus v. Okay. So, it will come with the opposite sign, that sign will be, yeah, if I put a negative sign, it will be positive. So, it is fine, right. Excellent. Now, a potential, if you realize, a potential typically is a surface which we can define a surface of the potential in the coordinate system. For a simple harmonic coordinate system, what is the potential? How does the potential look like? The potential looks something like this. So, we have displacement in this direction and energies in our potential energy V in this direction. So, it looks like this. Similarly, we can define a 2D potential, we can define a 3D potential, or we can also define, for a system of complicated particles, we can define a multidimensional potential. Now, whatever may be the definition, I mean, sometimes a multidimensional potential we cannot just draw it on the blackboard, it is impossible to visualize. But important thing is, V in this case, what was the form of V? It is half k x square. So, that means V, most importantly, the potential, whatever we wrote, whatever we can think of, is a function of the coordinates only, qk. It is not explicit function of time, and also these are not functions of velocities. Does not matter how fast the particle moves, the potential should not change, is not it? A simple harmonic oscillator, if it moves faster or slower, its potential function does not change. In certain cases, for example, in particle movement in an electromagnetic field, there is an effective potential which can be a function of velocity, but these are special cases which we will be not discussing here. But in general, for the systems we will be considering, the mechanical systems, where V is typically a function of Qk only, or basically I should not write Qk, but in general we can write V is a function of Q1, Q2, Qn. I mean all the generalized coordinates, no generalized velocity involved here. If this is the case, then del V del Qk dot will be unanimously equal to 0 for all k's, is not it? Because it is not a function of velocity anyway, so the partial derivative will vanish. So, without losing any generality, what we can do is we can use this property, and instead of t here we can also write t minus v. It is totally justified because del v del Qk dot will be equal to 0 anyway, it does not matter. But if we do that, we see what do we get here. If we do that, we are not losing anything, but we are gaining, because in a sense we can define a quantity, new quantity, which is okay, I do not need this anymore, I can go up from here. So, we can define a new quantity L, which is t minus v, and the equation what we wrote here in terms of Cartesian coordinates, which is the standard equation for, which is the D'Alembert's principle, now has a particular form. I am writing the summation explicitly, sum over k d dt of del L del Qk dot minus del L del Qk delta Qk equal to 0. So, this is the form, of D'Alembert's principle in the generalized coordinate system, what we get, what we see here. So, L is equal to t minus v, that means kinetic energy minus potential energy. So, T is your, so this is equivalent to of writing kinetic energy minus potential energy. Of course, kinetic energy and potential energy has to be defined in terms of generalized coordinates. So, we have a situation where T is a function of Q's, Q dots, or I would write an S, assuming, I mean saying that it is function of all Q, Q dots and time, right. I mean of course, kinetic energy might vary as a function of time, and V's typically is function of Q's only, right. Okay. So, this is the equation. Now, the beauty is here we have reached a situation where all the functions, all the in this form, if I write C1 and C2 and C3, I mean all the coefficient vanish only if x1, x2, x3 they are independent of each other. Now, we have reached a situation where these are my C's and these are my X's. All the X's are independent, because that is the definition of generalized coordinate. Generalized coordinate means the coordinate system which is, I mean all the it's a definition, I mean it's a set of coordinates which are all independent of each other. Now, if this is the case, we might as well equate each and every coefficient equal to 0. That means, we can get n number of equations, n is equal to, if you recall, 3n minus k, this many number of equations which has the form d dt of del L del Qk dot minus del L del Qk equal to 0. Okay. So, we have n number of such equations for our systems, and I will show you in a moment that these equations are exactly equivalent to the equations we get for a system using Newtonian dynamics, okay, Newtonian kinetics. But look at the advantage. Now we do not have to worry about constraints. We do not have to worry about the nature of forces. All we need to know is if a system is moving, okay, if a system is moving under any particular type of in a particular type of potential, all we need to know is a potential defined in a set of, first of all we have to look at the constraints, how many or rather we need to know how many independent coordinates we need, of course, that is something that is a prerequisite of the system. But once we know that, if we can define velocity, I mean potential and kinetic energy in terms of generalized coordinates and generalized velocities, then that is it, that is all we need. We can construct the Lagrangian. So, this L is called the Lagrangian of the system, and readily we can get n number of such equations. N is equal to the number of independent coordinates. So, this equation, this set of equations are called Euler-Lagrange equation or Lagrange's equation of second kind. Okay. So, this is where we end starting from, or I should not say end, but this is where we come starting from D'Alembert's principle. So, first we took first we removed all the constraint forces, got D'Alembert's equation, which is a long equation, single equation. From there we came to Lagrange equation of first kind, where we involved the constraint forces and constraint condition also in the situation in the system, and we got n number of independent equations. Or rather I would say 3n number of equations, out of which n numbers are independent, and then finally we have removed all the contribution from the constraints, and we have got small n number, which is equal to 3n minus k number of independent equations, which is sufficient to describe the system totally. Of course, we will see in a moment that this will also give you exact same second order differential equation as in the Newton case. So, we have to solve it, we cannot avoid integrations, we have to integrate it twice in order to get the full description of the problem. Now, there is another formalism which is called the Hamilton's formalism. There is an advanced version of it, Hamilton's Jacobi equations, which are essentially first order differential equations. But this will be too much for one course, so we are not covering Hamiltonian. I am pretty sure many of you will take advanced courses on classical mechanics, where the Hamiltonian will be covered in a great details. So, we are not going into Hamiltonian, we will be staying into Lagrangian, and we will build up from here. So, let us start by taking examples of systems. Sorry if I have taken too long to come to Lagrangian, but as a student when I tried, see, I can in the first class itself I can define there is a quantity Lagrangian which is nothing but t minus v, and we can get an equation of this form and we can start solving problems. That will not help in understanding why and how we have come this far. As a student I always had this problem of, during my student's life I never had access to so many textbooks. Nowadays we have lots of content in the internet, we never had that. So, I had a tough time understanding the concepts which will lead to this particular equation. So, if I have taken too long, that is totally for your good. Anyway, let us take examples. Let us start with a free particle. Yeah, that will be a good start. So, for a free particle, we have, what do we have? We have T, which is given by half. Okay, first of all, how many degrees of freedom a free particle has? The answer is 3. We have already discussed it many times, that we need 3 independent coordinates in order to describe the motion of a free particle. So, this 3 independent coordinate we might as well choose x, y, z, we can choose r theta phi, or we can choose any coordinate we can think of. Please keep in mind in Lagrangian also you have to integrate it, just like in Newtonian. It is just another way of getting your Newtonian equations of motion. Okay, it will not give you a new physics in terms of the final equations. So, it is always wise that you choose simplest possible coordinate system, keeping the symmetry of the problem in mind, just like we did in the Newtonian case, in order to get integrable equations. I can take any arbitrary coordinate system, any curvilinear coordinate system to describe the motion of a free particle, but that will not help me integrating it. I will get the equations. I mean, we do not have to worry about the constraint and all, we will get the equations. So, if we take free particle, it will be best if we take x, y, z coordinate system. So, your kinetic energy is x dot square plus y dot square plus z square, z dot square. I mean, frankly, kinetic energy is nothing but half mv square, and v is vx square plus vy square plus vz square, is not it, which is equal to this. And your v, I mean v as in the velocity, and your potential energy v is equal to 0 for a free particle, right. So, if I start by writing my Lagrangian, so my Lagrangian for system which is t minus v will be exactly equal to t equal to this half x dot, okay, there is an m, let us say free particle of mass m, x dot square plus y dot square plus z dot square. Okay. So, your Lagrange equation will be d dt of del L del q k dot. So, for each of this q k's we have to write one equation. So, for if there are 3 independent parameters, we need to have 3 equations. Now, in this case 3 equations will be identical, that is not that's not the issue, but we still have to write 3 equations to describe the system totally. So, the equation will be m by 2, see. So, m by 2 will be common from all, so we can just get rid of it. Del L del q k dot, I have to take a derivative with respect to generalized velocity. The first generalized velocity I encounter is x dot, second is y dot, third is z dot. So, when I take derivative, it will be 2 x dot, right, d dt of this minus del L del q k. There is no q dependence. Yeah, I mean there, in this Lagrangian nowhere this x and y and z comes. So, del L del q k for all the q k's. So, q k's are what? Right now the q k's are x and y and z. So, del L del x equal to 0 equal to del L del y equal to del L del z. So, we have a 0 equal to 0. So, my first equation is nothing but x double dot equal to 0, and just from the symmetry of the problem my second and third equation will be y double dot equal to 0 and z double dot equal to 0. And this is exactly what we have for a free particle. All the accelerations are 0. Free means that is no force is acting on them. So, the free particle has a constant velocity. If we integrate them, we have Vx equal to 0, Vx equal to constant, Vy equal to constant, Vz equal to constant. What are the values depending on the initial condition, that is it. So, all I am trying to tell you that it is the same equation, it is just another different way of looking into it. But this is very important, though you might ask, I mean if it is not giving us any new physics, why learning it? The answer is it is a different approach to physics. First of all, we do not have to think in terms of constraints anymore, and secondly, there are other advantages we will see later slowly and slowly. Secondly, this is a gateway to advanced physics, physical constructions like Hamiltonian is one thing. We will learn little bit of principle of variation integrals. So, these are all pathways which will lead to, I mean this is actually the gateway which will lead you to higher advanced physical formulations. So, it is important that we understand Lagrangian mechanism by heart. Okay. I hope you have this equation noted down somewhere. If not, please do that, because you will be needing it lot of time. Put it in front of your eye as much as you can, because this is something that you have to memorize by heart. Second equation, second case, central orbit. Now, in a central orbit, your kinetic energy T once again we have to keep in mind that we have to take the we have to consider the symmetry of the problem. Now, in central orbit, typically what happens is we have seen that without writing a single equation we can prove that the angular momentum L is constant. Okay. So, that means it is a planar motion, and in planar motion it is always preferred that we take r theta instead of x y. I mean, we can also take x y, but because central forces always give rise to orbits, for orbital planar motion it is always better if we take r and theta. So, we straight away start writing half m, v square will be what? V r square, which is r dot square plus r square theta dot square, right, and v is equal to v r. This is the potential function of the central force in question. So, your Lagrangian L, so L will be simply, I will just not write it again. Right. So, we already know the answer to this, but still I want to show you how to get to the equation of motion. So, the first equation will be d dt of del L del r dot, yeah, because r dot, what are the coordinates we have? Our generalized coordinates are q1 equal to r, q2 equal to theta, right. So, first equation it will be del L del r dot minus del L del r is equal to 0. Now, what is del L del r? Del L del r, see, we have one r here and this is a function of r, and the first, what is function of r dot? Only the first term. Okay. So, first term will give you d dt of half. So, half will cancel out, it will be m r dot. So, actually I can already take perform the second derivative operation. So, I can write directly m r double dot, no point wasting a step for that, minus del L del r. The first term will give you m r theta dot square, it is a partial derivative. So, theta dot term will be unchanged, minus v r, del L del v r will be there, which is nothing but your f of r. So, minus sign, just give me a second. Oh, okay, sorry. Yeah, so there is a minus sign here also, so it will be minus, which will be equal to 0. So, that means I can take this on that side and I can put the equal sign here, which will give you m r double dot. So, m goes out, we can take m common. So, it will be r double dot minus r theta dot square equal to f of r, and this is the standard equation for central orbit, we all know. For the second equation, this is for r. For the second equation, theta, del L del theta will be equal to 0, because nothing in this is a function of theta. Okay. So, second equation will be simply d dt of del L del theta dot, which will be equal to 0, because del L del theta is anyway 0, there is nothing is function of v theta here, and this will give you d dt of, what is it, m r square theta dot, right, equal to 0. Does it sound familiar? I mean, does it look familiar? Definitely it is. This is nothing but your angular momentum magnitude. Okay. So, the second equation gives you m r square theta dot equal to constant, and this is exactly what we know from our discussion or from our lectures on central forces, that this is one equation and this is the other equation. So, we could reproduce the two equations of central orbit starting from here. So, I'll stop the class here just by defining a single quantity which is called the cyclic coordinate. Just give you I'll give you an example. Theta in this problem is the cyclic coordinate, because theta does not occur in the Lagrangian explicitly. The generalized coordinates which does not occur in a Lagrangian explicitly are called the cyclic coordinate, which is in this case theta. Okay. So, we will see more examples of Lagrangian, how to solve problems with Lagrangian. We will take little more complicated problems. We have to add terms in the Lagrangian for frictional forces. We have to add terms for additional constraint forces if we have any. So, we will do that in the next lecture. Thank you.